Hi, and welcome to today's video. Today we're going to begin talking about complex numbers. So we're really going to dig in deep into what complex numbers are. We're going to do some graphing of complex numbers, adding and subtracting, that sort of thing. So first of all, we need to kind of know what a complex number is. So we're going to define complex numbers. A complex number is a number in the form a plus bi. So remember a plus bi, where a and b are real numbers, and a is the real number part and bi is the imaginary number part. Okay, so we're talking about complex numbers, real numbers, imaginary numbers. For a lot of students, this gets a little bit confusing, so be sure to watch carefully and pay attention to what's going on here. So a plus bi is the standard form of a complex number. So kind of notice here, if b equals 0, the result is, well, 0 times I is 0. So the result is just a real number with no imaginary part. And that's what we've been working with for a long time. And so these types of numbers are pretty common, that, they're things that you're used to. These are a little bit different. If a is equal to 0, the result is a strictly imaginary number with no real part. And so when we start talking about imaginary numbers, it sometimes gets confusing for students. And it takes a little bit of getting used to working with them, but they really are pretty easy once you give it a shot and work with them. So you might remember we've been over here in this area working with real numbers. So real numbers, we're going to now define them as a plus 0i instead of just a number. So remember, real numbers are split into rational numbers and irrational numbers, and we've been working with a lot of those. And here is a breakdown of real numbers. So now we have a bigger realm to work with. We have complex numbers. Complex numbers are all of the numbers in the form a plus bi. So we have an imaginary side of our complex numbers here that we've never really talked about before. So this is a whole new set of numbers that we're working with here. Imaginary numbers are in the form a plus bi, where b is not equal to 0, so it has to have some imaginary part to it. And then there are, in a smaller set, there are purely imaginary numbers with no real number part attached to them, so basically a is equal to 0. Okay, so here is a definition of complex numbers. Let's begin to look at them a little bit more in depth. So what is an imaginary number? Well, an imaginary number allows us now to take the square root of negative numbers. Remember, before, we've never been able to take the square root of a negative number because it didn't work before. But now that we have imaginary numbers in our toolbox to work with, we can now start taking square roots of those numbers. So I is defined as the square root of -1. So that's in a nutshell basically what imaginary numbers are, is numbers in the form where I is equal to the square root of -1. Imaginary numbers allow us just to do that, what we talked about, take the square roots of negative numbers. So in our first example, we're just going to simplify some square roots of negative numbers. So for example, in example A, the square root of -25. Well, remember the property of square roots that allows us to break a number up into its smaller components. So the square root of -25 is the same as the square root of 25 times the square root of -1. And we just got through talking about the square root of -1 is I, and the square root of 25 is 5. So the square root of -25 is simply 5i. Okay, so that's as easy as it is. For b, the square root of -12. Well, remember, we can simplify the square root of 12 down to the square root of 4 times the square root of 3. So I'm going to take the square root of -12 is equal to the square root of +12 times the square root of -1. And now the square root of +12 we can split up into the square root of 4 times the square root of 3, and then have the square root of -1. So the square root of 4 is 2, the square root of -1 is I, and the square root of 3 just stays as the square root of 3. Now, one thing I want to point out here, we typically put this I in between the 2 and the square root of 3 simply because if we write 2 square root 3i, sometimes it's hard to tell, is that I underneath the radical or not? So you really can't tell. So if we write it over here, there's a clear, it's clear that it doesn't go underneath the radical. So that's just one thing to be careful with here. We don't want to write it the I at the end. It's not necessarily wrong if we do. It's just unclear that way. Okay, so let's talk for a second about powers of I. So we know that I is the square root of -1. What about I squared? Well, I squared is the square root of -1 times the square root of -1, which is the square root of -1 squared. Well, we know that the square root and the square kind of cancel each other out. So the square root, or I squared, is just -1. I cubed. Well, I cubed we could rewrite as I squared times I. And we just talked about the square, that I squared is -1. So it becomes -1 times I, which is simply -I. So I cubed is equal to -I. How about I to the fourth? Well, I to the fourth is I squared times I squared. I squared is -1, so -1 times -1 is +1. So I to the fourth is equal to +1. Okay, now what happens when we get to I to the fifth? Well, I to the fifth is I to the fourth times I, and I to the fourth was just 1, so it's 1 times I. We get back to just I, which is I to the first. Okay, so notice that powers of I repeat every 4 powers. So if we were to go to I to the sixth, it would be the same as I squared, which is -1. I to the seventh would be I cubed, which is -I. Also, thinking backwards, if we go backwards, I to the 0 power would be the same as I to the fourth, which is 1. And we've already discussed before that anything to the 0 power is always just 1. So I to the 0 still fits that same pattern for imaginary numbers as it does with real numbers. So we're going to use that information now to find, for example, I to the 32nd power. So here's how we can go about that. If we divide, because we know that it repeats every 4 powers, if we divide 32 divided by 4 and use the remainder, that will really help us out. So 32 divided by 4 is equal to 8 with a remainder of 0. And so since this remainder is 0, it's the same as r to the fourth or even r to the 0. So I to the 32nd is equal to I to the fourth, which is just 1. Okay, how about I to the 50th? Well, if we take 50 divided by 4, we get 12 with a remainder of 2 this time. So it's going to be the same thing as I squared, I to the second power, which is just -1. Okay, last one, I to the 15th. Take 15 divided by 4. That is 3 with a remainder of 3. 3 times 4 is 12. 12 plus 3 would be 15. So that remainder is 3. So I to the 15th is the same as I cubed, which is just -1. Okay, so hopefully that helps you to break those down smaller if you need to. Okay, so now let's talk about adding and subtracting complex numbers. The nice thing about adding and subtracting complex numbers is it's just like adding and subtracting regular algebraic expressions. So we combine like terms just like any other algebraic expression. So in this example, we're going to add and subtract some complex numbers. So simplify the complex expression, write answers in standard form. Any of these, even if I don't put write answers in standard form in the directions, just get into the habit of writing them always in standard form whenever possible. Okay, so in example A, 3 plus 2i plus 7 minus 6i. So this is a complex number, this is a complex number. I just put the parentheses in there to show you that we're adding 2 separate complex numbers. So we don't really need those parentheses though, so we can just write it out. 3 plus 2i plus 7 minus 6i. And now, remember the commutative property of addition says we can change the order of things. So I'm just going to switch this order around so we kind of have things grouped together. Notice we have the real numbers grouped together here. We have the imaginary numbers grouped together here. So if we take 3 plus 7, we get 10, and 2i minus 6i is -4i. Okay, so it really is just as easy as any other algebraic expression. Okay, so down here, the one thing we have to be careful of, since this is in parentheses here, we do have to distribute the negative sign. So 5 minus 8i minus 3 plus I. So if I started out here, get rid of the parentheses. 5 minus 8i, here's this one, minus, and we have to distribute the negative sign, so minus 3, and then minus I. And once again, use that commutative property to switch some things around. So 5 minus 3 minus 8i minus 1i, or just I, gives us 5 minus 3 is 2, negative 8 minus 1 is negative 9. So 2 minus 9i. Okay, next one. 6 minus 2 minus 7i plus 3 plus 4i. So again, just a little longer problem, but it really is the same sort of idea. We're just going to distribute the negative 1 here. So 6 minus 2, and then negative 1 times negative 7 is plus 7i. And then we can just drop the parentheses here, plus 3 plus 4i. And now, once again, I'm just going to switch the order of some things here. So we have 6 minus 2 plus 3, plus 7i plus 4i. So 6 minus 2 is 4, plus 3 is 7. 7i plus 4i is 11i. So it really is just as easy as combining like terms, just like any other algebraic expression. Okay, so now let's talk a little bit about graphing complex numbers. So complex numbers have their own number plane. It's called the imaginary number plane. And it looks just like the regular coordinate plane that we normally work with. So the what we normally call the y-axis is the imaginary axis, and the x-axis is the real axis. And so just like if we were to graph, say, the point 4, 2, where we go to the right 4 and up 2, same sort of idea here. So we're going to plot complex numbers just like xy coordinates. So we're going to move a units on the real axis, and then we're going to move b units on the imaginary axis. So if we were to plot 4 plus 2i, we would just go over 4 and up to 4 plus 2i. Okay, so down here, plot each number on the imaginary plane. So the first one is 4 plus 3i. So again, we're going to go 4 units on the real plane, or real number line, 1, 2, 3, 4. And then we're going to go up 3 units on the imaginary line. So 1, 2, 3. So here is 4 plus 3i. Okay, negative 6 minus 3i. So if we start out here, we're going to go 1, 2, 3, negative 3. And then minus 6i, so down 1, 2, 3, 4, 5, and 6. So negative 3 minus 6i. So that's really all there is to graphing complex numbers. Okay, the last thing we're going to talk about here is the absolute value of a complex number. So remember, absolute value is simply the distance a number is from 0. So for example, if we had just a real number, the absolute value of 5 is just 5. The absolute value of negative 5 is just also 5, because it's 5 units away. So the absolute number is, absolute value is just its distance from 0. And so if we were to look at the absolute value of a plus bi is equal to, in this case, the square root of a squared plus b squared. And I'm going to show you here on the next why that is. So if we just think about the number, the coordinate 3, 4. So if we go over 3 units and up 4 units and plot that on the regular number line, regular coordinate plane, what is the distance that 3, 4 is from the origin, from 0, 0? So we can think of using either distance formula, or it's almost like Pythagorean theorem. So since we're looking for distance from the origin, this is 0, 0. So if we use the distance formula, x2, which is 3, minus x1, which is 0, squared, plus y2 minus y1 squared. So 4 minus 0 squared. So here is the distance formula right here with our coordinates plugged in. So if we simplify, 3 minus 0 is 3, 3 squared is 9, and 4 minus 0 is 4, 4 squared is 16. So 9 plus 16 is 25. Square root of 25 is just 5. So this distance here is 5 units away from the origin. Okay, so we can use that same sort of idea to find the absolute value of each imaginary number. So here I once again wrote the formula for it. Remember, it's the absolute value of a plus bi is equal to the square root of a squared plus b squared. So if you just think of Pythagorean theorem, a squared plus b squared, and then we have to take the square root of that to find the length of the hypotenuse. Okay, so it's really related to that same sort of concept. Okay, so the absolute value of 4 plus 3i. Well, those numbers look familiar. They're kind of from the last example. But just to illustrate, it's the square root of 4 squared plus 3 squared, which is 16 plus 9. So the square root of 25 is just 5. Okay, so let's do another one here. Absolute value of 3 minus 6i. So it's the square root of 3 squared plus negative 6 squared. So 3 squared is 9, negative 6 squared is 36. 9 plus 36 is 45. And so I went ahead and I wrote 45 as 9 times 5 again. So it's the square root of 9 times the square root of 5. And we can find the square root of 9, that's 3. So that simplifies down into 3 square root 5. Okay, the last example is a fairly straightforward one, the absolute value of 7i. Well, think about where 7i would be on our imaginary plane here. It would just be up here. It would be right on the axis because it's 0 plus 7i. So that distance is going to be really easy since it's on the axis. It's just 7 units away. But if we use the formula, 0 squared plus 7 squared is 0 plus 49, which is the square root of 49, which is once again just 7. So again, if we square it and then take the square root, we get back to where we started from. And remember, since we're talking distance, our answers are always going to be positive. Remember, we talked about if we take the square root of a number in an equation, we get plus or minus. But since this is a distance, it's always going to be positive. Okay, well, that's all I have for you for today. I hope you found this helpful and useful. And as always, I hope to see you again soon. Thank you for joining me.